Today we're going to get introduced to our first set of reaction types for our AP chemical reactions. We're going to look at both addition reactions and decomposition reactions. Now, you'll see addition reactions often called things like composition reactions, perhaps synthesis reactions. And you'll see it in AP sometimes, but addition seems to be the most common. Some might disagree, but we're going to call them addition reactions. Addition reactions are when we take two or more elements or compounds and combine them together to form a single product. The most important thing here, one of the most important things, is to know your common oxidation states. Take, for instance, the first example. A piece of lithium metal is dropped into a container of nitrogen gas. So we know we're dealing with lithium. We know we're dealing with nitrogen gas. Now, in addition to knowing what those charges are, those oxidation states, we also need to know our diatomic elements. So don't forget our hydrogen 7, the hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are our 7 diatomic gases. So we've got a piece of lithium along with nitrogen gas, which as a gas, as a free element, is N2. We're going to react them together to form a compound. If you've got two elements and that's all you're starting with, then there's really nothing else you can get in the end except a compound. So we're going to put lithium and nitrogen together. Now keep in mind that lithium has a +1 oxidation state. Nitrogen is a -3 when it's in a binary ionic compound. So if that's true, we're going to need 3 lithium atoms to balance that 1 nitrogen atom. So there's the overall reaction, skeleton equation, if you will, but don't forget we need to balance it. So looks like we're going to need 2 of our lithium nitride molecules and 6 actually of our lithium. So there's your final reaction for that. So what if you've got 2 compounds that are reacting together and no water's involved? They're not solutions or anything, so how's that going to play out? Well, if we've got SO2 and we're reacting it with calcium oxide, one of the biggest things to notice here is that you're dealing with a molecular compound and an ionic compound. So you're not going to get double replacement. And even if you did try to do double replacement, you would end up getting the same thing you started with because they're both oxides. So what we will find in this situation then is that we're going to get those two combined together. Now that's when you have to start thinking, what have I seen that would contain calcium, sulfur, and oxygen? And that's where experience in chemistry comes in handy, because hopefully you'll remember that the metal always goes first in the compound. And when we're dealing with sulfur and oxygen, we've got sulfur and 3 oxygens here. Well, we hopefully remember that we have a nice polyatomic ion, sulfite, that is SO3. So we combine those together and we think about what kind of compound we could get out of that. Calcium's a +2, remember, and if you look up sulfite, or hopefully remember, sulfite is a -2. So that's the reaction for, or the equation for that particular reaction. Now the next one, the gases boron, trifluoride, and ammonia are mixed. So we've got BF3 and NH3. We'll get way more into why this occurs when we get into our acids and bases. This is actually going to end up being a Lewis acid-base reaction. But for now, guys, you just got to memorize this. You've got the boron compound and the nitrogen compound. Somebody in the AP world loves this reaction, because all they do to show this is to show that the boron and the nitrogen join together, and whatever's with the nitrogen at the end, and usually they write it this way. I know it looks a little backwards, but they want to emphasize that the boron and the nitrogen are the ones that are connecting there. So if you get a boron compound and a nitrogen compound, it's going to simply hook together. Carbon dioxide, the next one. Carbon dioxide is passed over solid sodium oxide. The nice thing about addition and decomposition reactions is we don't have to worry about what's going to ionize. So we don't have to worry about a net ionic reaction on these. So carbon dioxide has passed over solid sodium oxide. What do you notice about the types of compounds? When you see two compounds, you try to do double replacement. You realize you can't do double replacement because, for one thing, one of them is molecular and one of them is ionic. And um, if you tried to, you'd get the same thing you started with. So this is an indication that you're dealing with an addition reaction. And so we're simply going to see what we can form out of that. See if you can do it on your own real quick and then come back to this. So hopefully you remembered from the previous example that the metal comes first. Don't carry over subscripts unless they're part of a polyatomic ion until you get this worked out together. But what have you seen with carbon and oxygen? Well, the carbonate ion. And so what about charges on this? Sodium's a +1 and carbonate's a -2. So when you write this formula, you're going to need 2 sodiums for this. And it works out really well because that balanced it anyway by putting in those 2 sodiums. So that's another type of, or another example of a type of addition reaction. Now what about decomposition? Decomposition, in this first example, we have a compound. When we have a decomposition reaction, we've got a compound that breaks down into 2 or more elements or compounds. Usually they'll say something about heating it, electrolysis, or using a catalyst, something like that whenever they talk about it. Sometimes they'll just say they break down or they decompose. In this case, it says sodium chloride is electrolyzed. So if we've got NaCl, no water's mentioned. We don't have to worry about the water. And it's electrolyzed. It's going to break down. Now think about what it's going to break down into. It's going to break down into its elements, not its ions. So we're going to get sodium and we're going to get chlorine. But remember, chlorine's one of our diatomic elements, so it's going to need a Cl2 here. So we've got sodium metal, chlorine gas, and now we need to balance it. Looks like we need a 2 here and a 2 here in order to get this balance. So that's the reaction. We've got to break it down into 2 elements, 2 or more elements, not ions. So remember that whenever you're breaking those down. In the next example, magnesium carbonate is heated. It gives you the rule up above it that if you have a metal carbonate, in this case magnesium carbonate, and you break it down, it's going to yield a metallic oxide and CO2. Carbonates, when they're heated, pretty much you're always going to get CO2 out of it. So we get Mg with O, and since magnesium is +2 and oxygen's -2, that's the formula. And then CO2 is also produced. So that's the equation, and it balances already for this particular decomposition reaction. Another common one you'll see on the AP test is the hydrogen peroxide reaction. They love hydrogen peroxide. When hydrogen peroxide breaks down, it always breaks down to form, and that's just something you just probably need to memorize, H2O and O2. That's the part of it that's doing the sterilizing or acting as an antibacterial. It's producing that oxygen. So if you let a bottle of hydrogen peroxide sit too long, and if you let it sit out in the light, it'll happen really fast, you're going to get water. It's going to go bad because you're going to have water. It's going to build up oxygen gas. So balancing this looks like we need to have a 2 in front of the water and a 2 in front of the H2O2, and that's going to balance this reaction. Another specialty one, sometimes when it says something breaks down, you try to think of what kinds of gases might be produced. There is a rule for this. If you take ammonium carbonate and you strongly heat it up, as it says up above, it tells you exactly what it's going to produce. But if you look at the formula, you can get a good clue. You're going to get NH3 whenever ammonium is heated up. You're going to get CO2 when a carbonate is heated up, and we've got some nice water left over in the middle when you start balancing this out. That's produced as well. It looks like to balance this, we pretty much just need a 2 in front of that NH3, and that's going to balance it. So that's another one that you kind of have to memorize, but it's really not too bad when you, again, look at what's in that compound. You can kind of figure out what it is. We have seen this before in our lab, looking at the formation. If H2SO3 is formed in a compound, or if it breaks down, it's going to decompose into SO2 and H2O. The same thing's going to happen if you have carbonic acid. Carbonic acid also, or excuse me, hydrogen carbonate would be a better way to say it, decomposes when it's produced or when it reacts into CO2 and H2O. So those are ones that you need to remember because they're going to happen quite often in our AP reactions.